In this part, we will discuss data structures. For today, we have three main goals. 1. Understand what do we mean by data structure. We will discuss two main types of arranging data in computer memory. And finally, we will see the benefits of using data structures for making our programs more efficient. Let's bring our attention to the computer memory, which is called RAM, Random Access Memory. This is the place where we store our data during program execution. We can visualize computer memory as a grid of cells. Each memory cell contains 1 byte of data. The cell has its own name or address, normally expressed as a hexadecimal number, but we will use here decimals for the simplicity of explanation. If we want to store a single value, such as this integer 12, we would use 4 bytes of memory. 4 consecutive bytes of memory will be occupied by the bits representing number 12. In our program, we will refer to this memory location by name. In this case, value 12 is stored in 4 consecutive bytes starting at memory address 8, and the named placeholder I refers to this memory location. If we need for our program to store more than a single value, for example, this sequence of integers, we can arrange the data in memory in two alternative ways. The first way to arrange the sequence of values is to place each value one after another, starting at some memory location. Such arrangement of data is called an array. The first element of the array can be accessed directly through the address stored in the variable a. It is important that in the array, all values, all elements have exactly the same size. Why is that? If we know that the first element is at memory location 8, we can pre-compute the location of any element by its position in the array, which is called index. And then we can go directly to this memory location and access the desired element. For example, in this case, each array element occupies 4 bytes. If we want an element at index 2, we multiply 4 by 2 and add 8 to the address of A. This gives us memory location 16, where we go directly to this memory location and read the desired element A at index 2. So this will be an example of a data structure, the simplest possible way of arranging sequence of values in computer memory. Alternatively, we could store a sequence of value in a different data arrangement, which is called a linked list. In this case, each value is stored together with something which is called the address of the next element. For example, here the first value of sequence, value 2, is stored in memory location 8. Next to it, we find the address of the next element in this sequence, the address 36. If we jump to address 36, there we will find the next element of the sequence, which is 14, and next to it we will find the address of the next element. And so, by having just the address of the first element, we can recover the entire sequence by following this sequence of links. Each combination of the value with the next pointer is called a node, and the linked list is an arrangement of nodes. As you can see, in this case, our sequence will occupy more space. However, the values do not need to be arranged consecutively. So that is the difference between the array arrangement and the linked list arrangement of values. So what is special about this arrangement, about linked lists? First of all, the entire sequence is defined by the address of the first node, stored in variable t. Other elements can be recovered by following the sequence of links. Unlike in the array, we now cannot access the element directly by its position in the sequence, by the index. We need to follow the sequence of links because we cannot pre-compute the address of the desired element. And finally, unlike in the array, we do not need to always have this consecutive memory chunk to store a big amount of values, and we can store new values anywhere in the RAM, and as such, we can grow our lists indefinitely as long as the memory permits. So, these are the simplest ways to arrange a sequence of values in computer memory: an array and a linked list. From these simple arrangements, we can create more complex data structures. For example, we can create a tree. In this arrangement, along with each piece of data, we store two memory locations, one for the left child and another for the right child of the node. This way, we can generate a binary search tree used for efficient search. In this tree, the data is arranged in such a way that for each node, all values in its left subtree are smaller than the current node, and all values in the right subtree are greater than it. So if we search, for example, for 99, 99 is greater than 8, go to the right child. 99 is greater than 14, go to the right child. And finally, we found 99. An array, a linked list, and a linked tree, which we just saw, are all examples of data structures. Data structure is a way of organizing several variables in memory in such a way that they can be accessed and manipulated efficiently. Let's look at some more examples of data structures. Here, for example, is a binary heap. A binary heap is a tree where for each node all the values in both its children are greater than the value of this node. For example, pick node 1. As you can see, all the values in both subtrees of 1 are greater than 1. If you pick 4, both subtrees of 4 are greater than 4. You see? However, searching in this tree is not possible, unlike in the binary search tree that we saw right now, because there is no way to distinguish between right and left subtree. However, this particular data structure is used for efficiently computing the minimum in the sequence, because the minimum value is always located on top of this tree in its root. Here is another example of a data structure. This time we use an array with direct addressing in order to store a character at the position of the array which is equal to the value of this character. This can be used, for example, in order to find out which character is repeated first. So when we see character C, we mark the position 2 of the array, which correspond to character C. When we see character A, we mark the first position of the array, assuming that our characters are marked starting from 0. Then we see character B, so we mark position 1 of this array, which corresponds to character B. Next, we see character A, we check position 0, we see that A is already in the position 0, and that means A is the first repeating character in this example. This idea of storing values in the array at a position which are somehow related to the values themselves is used in a data structure which is called hash table, where we can hash and store not only single characters, but any type of objects. As a final example, consider the structure of nodes where every node may be connected to any other node. This arrangement is called a graph. It's a very useful data structure which can be implemented by using a two-dimensional array or a list of lists. So as you can see, everywhere we use the ideas of either an array or an idea of linked nodes. Is there a perfect data structure, a super data structure that is the best for any task? The answer is no. Each data structure is optimized for a particular task. That's why there are so many different data structures, and one of our goals is to learn which data structures to use and when. In this example, for example, if we only want to find the minimum in the sequence of values, we could arrange elements into a binary heap. And in this case, we would be able to find minimum just in one step. However, binary heap is not good for search. If we also want to do search for an element, we probably would use a binary search tree. We can also find the minimum in the binary search tree. However, that will not be accomplished in one operation. We would need to search at least as the height of the tree. Finally, I wanted to illustrate why it is so important that we learn data structures. We study data structures in order to improve the quality of our programs. The choice of the suitable data structure will make all the difference between a failing and successful program. As an example, consider the problem of finding the word with the highest frequency. The input is a text. The text is converted into the list of words, all different words that occur in this text. And our goal is to tell which word is most frequent. There are many possible solutions to the problem of finding the most frequent word. So the input to our counting program is the list of all words extracted from a given text file. The output is the largest count of the most frequent word, together with the word that gave us this count. So this is the most obvious solution to this problem, which is we declare two variables, two accumulator variables, max count and the word that gave us this count, and then we iterate over all words in the all words list. We look at a given word, and for each such word,
we check all other words in that list, and if we found the word which is the same as our current word, we increment its count. Once we finished counting the occurrences of the current word, we see if its count was greater than the max count so far, and we update max count and the word that gave us this count. And at the end, we are going to have our most frequent word. We can also solve this problem by using a specific data structure, namely a hash table, which is used to implement the Java class hash map. So in this solution, we will store every word we encounter inside the hash map, together with its count. So each time we see the word, we check if it's already in the hash map, and if it is, we get back its count. If it isn't, we set the count to 0, and we increment the count by 1 for the current encountered word. Once we updated the count, we put this pair back into the hash map, and before we move to the next word, we also check if our current count is already exceeded the max count or not. And if it didn't, and if it did, then we update the max count and also the word that gave us this max count. So it might seem to you that these two programs are very similar and there is no fundamental difference in these two solutions. However, we can check the speed of these programs. We can check the performance of these two solutions by just running these two programs. So we are going to run them on the file, which contains about 33,000 words. And we will ask first naive program to count, and then the program which uses a hash table to count. So we run that, and then we see the following results. Okay, so our naive program finished in about 4 seconds, and our hash table program finished is in about 40 milliseconds. This is about 100 times faster. The second program is 100 times faster than the first one. And that already, I hope I persuaded you that using the specific data structure, the data structure which is best for solving this particular problem, will make your program much faster. And that is actually one of the goals of this course, is to teach you which data structure to use for which problem. Two questions remain. One question: will the hash version always outperform the naive version 100 times faster? And the second question: should we always implement all different solutions using different data structures and algorithms, and then run those solutions to compare their performance? The answer to both these questions is no. If we increase the input size, or if we use a different input, different by nature input, it might be that the second program is not going to be 100 times faster. And also, we do not need to implement all possible variants of the solutions to the problem in order to tell which solution is better. We are going to learn algorithm analysis tools that will allow us to answer both these questions and to evaluate the quality of our solution even before we implement any of them. So we are going now to discuss some introduction to algorithms.